welcome back. Today we are going to talk about phase changes of alloys. We've reviewed some information on phase changes of pure substances like elements, gold, silver, that sort of thing, iron, and about compounds like water, salt, that sort of thing. They all behave in a certain way. They have melting points, they have boiling points, they have vaporization points, they have freezing points. The question is, do mixtures? Well, the answer, no. With one exception. We'll talk about that as we go through this. So, first thing we're going to do is we're going to talk about how phase changes in an alloy. Alloys are mixtures, so they're not chemically combined, right? So we have alloys as mixtures. Alloys have a melting range. It's a temperature at which it starts to melt and a higher temperature at which it completes melting. So it stops melting. So it's basically going to be, it could melt between here and here. Okay. What's going to happen is parts of it are going to melt and parts of it are going to stay solid, and it's going to create a slush, which is a mixture of a solid and a liquid. If you want to think slushy, like what is it? It's ice, solid water, and liquid, usually flavored liquid, but liquid water, combination of the two. So slushy, it's a combination of solid and liquid. Now, how much slush you have, how much of a range it has, is going to vary on the temperature at which it's being heated at, and also what the percent composition is. And we've seen this with that lead tin spot lab. When we look at that lead tin spot lab, we created a graph that sort of had a V in a shape, right? So this is actually the lead tin phase diagram. You can see down here, this is 100% lead, and this is 100% tin. And as you can see, that there is this area of black right here, and this is where it could melt, but not necessarily. So those are your ranges for the different compositions. So for an alloy that is 20% tin and 80% lead, you will see that it could melt anywhere between about 198 and let's say 290. That would be where that can melt. Ooh, okay. So for the most part, you have these ranges for the different alloys, except for this one spot right here. What is that spot? Well, that is a special composition. That is the point where the alloy actually acts as a pure substance, and it will have a melting point instead of a melting range. So that is called the eutectic composition. That's a mixture that acts like a pure substance. It has the lowest melting point on that whole range, and I'll go back for a second. Okay. As you can see, again, right there, let me put that circle back up. That is the place where it's absolutely going to be turning into a liquid. Okay, so that's our first one with our lead tin spot. We saw number 8, but really, again, it should have been around number 7, 61% lead. Okay, and then it has, the eutectic composition has the lowest melting point. Okay, the eutectic composition is going to be different. Like I said, with lead tin, it's about 61% lead. Each alloy, depending, is going to have its own eutectic composition. And that's what we're going to look at today, is reading these binary phase graphs, reading those diagrams, and determining the different eutectic mixtures and eutectic temperatures for those different alloys. Okay, so I'm going to go ahead and move forward, and we're going to talk about the parts of a graph. Now, one of the most important parts is something called the liquidus line. Any ideas what that might be? You guessed it, it has to do with liquid. It is the line that separates the solid or slush from the point where the alloy is a complete liquid. So the liquidus line is is the line where it's only liquid above that point. And we're going to see that right along the top of the slush zone. So that's your liquidus line. Everything in this area is liquid. That's what we're going to end up with, okay? So let's go back. That's the liquidus line. It's only liquid above that line. The solidus line, any guesses? You've got it. It's where the solid is, where it's only solid. This time it's actually below the line because again, we're talking about temperature and ranges. So the liquidus line, only liquid above that line. Solidus line, only solid below it. So there's your liquidus line again. And then your solidus line is going to be where the slush, right below where the slush starts. Where does it start melting? So there's your solidus line. And any of the regions right here, that's all going to be solid. Okay, so again, this is lead tin, so this would be their solid spots. These are where they've turned into liquid and the students are playing around with them. This black line, again, does represent the slush for that. And what about this one? What is that called, that green spot? Okay, that is our eutectic point. All right, the eutectic point is the lowest melting temperature. The eutectic point indicates where the eutectic composition is. So these are the parts of our binary phase change graph. You've got your slush there, that zone where you have both liquid and solid. Then you have your liquidus line that shows us where everything above it is completely liquid. Your solidus line where everything below it is completely solid. And then that point called the eutectic point that tells us where that alloy, that mixture, actually acts like a pure substance and has just one melting temperature instead of that range. Now, if you notice, there's sort of something happening right here. Okay? The solidus line and liquidus line are coming together. The solidus line and the liquidus line touch in three places. The first line is going to be the melting point of the pure substance on the left side of the graph. So you have your melting point of pure lead. That's going to be one point where the solidus line and liquidus line meet because, again, you have that pure substance, and so it's going to have just one temperature that it melts at. The other side, you've guessed it, is going to have that melting point of your other pure substance, this time tin. We already know that it's going to do 232 degrees Celsius. It's going to melt at 232 degrees Celsius. And so you have the melting point at that with the pure substance, and it's going to turn from liquid into solid, or from solid into liquid like that. You could do the other way too. The last point where the three reach is going to be our eutectic point, where those two lines meet between solidus line and liquidus line. So those are the three places where you have the alloy acting as a pure substance when it's either really pure substance because 100% of either element, or when you have your eutectic mixture. Might be a couple of other things you're wondering about with that graph. For example, what is this gray area on this side? Is that the solid? Is that the liquid? Is that slush? What's happening? Well, it's actually parts of your phase change where they're changing crystal structures, not necessarily from solid to liquid, but from one BCC, FCC, HCP, all of those, okay? What's happening is that every point on this graph is at an equilibrium state, meaning it's in its least energy consuming state, okay? So it's most stable. In this case, you're going to have different structures, or it could be a couple different structures. Something is metastable when it becomes locked into position between two in a phase change between two phases. For example, steel, when we quench it, it gets locked between the FCC and BCC phase change to give us that stronger steel. So that would be something called metastable. So you're actually sort of manipulating this graph here to work out how to use those temperatures to your advantage. Okay, so let's take a look at a couple of other phase change graphs. This is a phase change graph for the binary phase change for bismuth and tin alloy. Okay. So you'll see that you have this line right here. This is your liquidus line. Okay, that L represents that it's liquid all above there. Here is your solidus line. It's going to represent that it's all solid right there. And then you're going to have your L plus S, that's liquid and solid. That's your slush zone, right? So what is this right here? This is your eutectic point. So it's going to tell us that the eutectic composition for bismuth tin is about 55% bismuth, therefore 45, 100 minus 55, 45% tin. So that's your eutectic composition right there. Where does it meet? And then the eutectic temperature is just under 150, let's say 140 degrees, if you look over here. Again, you have those regions over here, your homogeneous mixture of different phase changes, the crystal structure, not from solid to liquid, but from different crystal structures there. Okay, another example, we have silver and copper. Okay. This one looks a little interesting. It's sort of it's the opposite. We have the alloy at this end, a little bit more the V down here. So here is your eutectic point. You've got your liquidus line at the top, okay, and everything above it's liquid. You have your solidus line down here. Everything below it's solid. Now, what I want you to notice is this says A plus B. That's going to be a mixture of your different crystal structures, crystal structure A and crystal structure B. And then you have your two different types of mixtures over here with just A or just B of that phase. Here is your eutectic point, okay? And it tells us right on the graph that the eutectic composition for silver and copper alloy is 28.1% copper, because it has it right here, so 28.1% in copper, which means it's about 71.9 of silver. Okay, so there's your eutectic composition, and your eutectic temperature is about, what should we say, 790, maybe 780 there. Okay, and then let's do one more. Ooh. What's this one? That looks sort of intense, right? Okay, well, it's chromium and nickel. So here's chromium at the bottom, and this tells it nickel, Ni right there. Here is your eutectic point right there in the center, about 55% chromium. Okay, at 1345 degrees Celsius is the temperature. Your liquidus line is a little different this time, but it's still right there. There's your solidus line, and then your two different phases of your crystal structure there. Okay, but if you think that one's bad, take a look at this. Aluminum and zinc. Actually, it's not that bad if you know what you're doing. Your eutectic point is going to be about right here, but what we see is all those different types of crystal structures that you can have. So we're not just doing BCC or FCC or from BCC to HCP, that sort of thing. These have several different crystal structures that they could take. Okay. All right, so that's it for today. What you're going to do now is go ahead and hop onto Nearpod and try this for yourself. All right, have a good one.